All right, thanks for coming, everyone. So this week we'll be talking about convolutional neural networks. Um, so we'll start off looking at some of the different tasks that you can do with convolutional neural networks, just a few subsets of them, but it will build the building blocks into what you can make out of these convolutions. So a basic one, we've seen this a few times actually already, image classification. So you take in some image and then you pass it through some model, right now just a black box, and then you get some outputs and it classifies 1,000 different classes or something like that, saying this is a bike, this is a dog, this is something else. Um, so another task that you can do is object detection. So instead of classifying just one thing in the image, you're figuring out like where are the things actually in the image and draw a bounding box around them. And you can have multiple different classes, but then you're also trying to find all of the different instances and the bounding boxes of them. Um, and then another one is image segmentation. So this is even more specific than object detection. Object detection is just here's a bounding box that encloses the thing that you're looking for. And image segmentation is trying to say at the pixel level, label every single one, which class it is. So you can do this with binary segmentation, like they show here. So it's just like here's background and here's animals, for example. Or you could have it even more specific where you say this is one certain animal, this is another certain animal, and then in the back there's trees or something like that. And you could segment that all separately too, and it would just all be different classes that you're outputting there. Um, so looking at networks for images, a very, very common size that a lot of people use is 224 by 224. If you look at most image models, they've been trained at that resolution. Lately, people have been pushing for larger and larger, but that's kind of the standard benchmark for if you're trying out an architecture, most people try 224 by 224 so that it's an even comparison with all of the other models that have been trained before. So if you look at what that actually adds up to, it's this huge dimension count. And so if you tried to handle this with a fully connected network, um, you end up with this ridiculous amount of parameters, even for a relatively small image. So if you do 224 by 224, and then you have an input and an output that is of that dimension, you end up with just a huge count. And so 22 billion is within our range now, but back in the day, definitely not. So people had to figure out how do we do something efficiently enough that you can actually uh, do everything usefully. Um, and so one of the problems with doing this with just a regular, fully connected dense network is that you're learning the patterns very specifically to where they are in the image. So if you're trying to detect a cat and then you just shift the cat 5 pixels to the left, it has to learn a completely new pattern for that because it's looking at completely different inputs and it doesn't understand the relationship there. Um, and so ideally, we want networks that are stable under transformations like that. So if it's rotated a little bit, if it's shifted a little bit, if it's blurred, all kinds of these different conditions can happen, and it's not a very useful network if you shift it 1 pixel and then it just completely doesn't understand what's in the image anymore. Um, so that's when convolutional networks come in. And so the thing about this is that you have parameters that are only looking at a small local patch, and then it's sharing that across the image. So it's looking for the same pattern everywhere. And we'll look at how this builds into that in later slides. Um, so there's this concept of invariance, and this is the premise that you want it to if you have some input and then you get some output from it, and then if you have some input and you blur it a little bit or shift it a little bit or do some other augmentation that you believe preserves the meaning of it, you want it to get the same result out. Um, so like the example with the cat, it should be able to still understand that if you blur it, for example. You want it to get the same result either way. So they have this example here, and I mean, when I was originally looking at it, I couldn't even see the difference at first. So this is just something that's been shifted a little bit. And so as humans, we look at this and we go, okay, that's a snowy mountain, and we're able to figure that out. But if we used a fully connected dense network, you might shift it a tiny bit, and then it just goes, I don't know what this is anymore. Um, and so that's where convolutions become very useful because you're robust to that. Um, so that was invariance, and then equivariance is related, but it's basically saying if we have some transformation on the input, we want that transformation to also be reflected equivalently on the output. So if you flip it horizontally, for example, and you're outputting one of those segmentation masks or those bounding boxes, you want it to also flip those. So then the mapping is correctly paired with the pixels as well. So here's another example of that. They have this room and then they're segmenting all of these different things inside of it. And so if you shift it a little bit over like they've done, you want it to still be able to find all of the pixels for the carpet and the table and the plants and stuff. So we'll start by looking at 1D convolutions just because that's the simplest building block we can look at. So imagine we have this sequence x1 through xi, um, and then we take the weighted sum of the neighbors. So let's say that we're doing a convolution with a size of 3. So we have weight 1, weight 2, weight 3. So this has a kernel size of 3, and then we're applying it to 3 inputs at a time. So this is what it looks like. You have your sequence of inputs, and then you have your convolutional filter that is applying to all three of these at once, and then it's a weighted sum of these to become this output. And so with the convolutions, what you do is you start at the beginning and then you slide through, and so you're applying these same three weights for all of the different inputs. Um, so this is saying that it's equivariant to translation. So if you had this set of inputs, X1 through X3, and then you had the same thing, X4 to X6, it would get the same output because these weights are being applied in exactly the same way. Um, so one thing you might notice is on this, we actually started at X1 and then we're outputting directly into Z2. And so how do we get Z1? Well, what some people do is they will do zero padding. So then you just pad a little bit at the beginning, a little bit at the end, and then you're able to get exactly the same size output as you did input. Um, and so one alternate option is you can do valid convolutions, which is saying I'm not going to do any padding. I'm just going to reduce my output. So this is nice because when you do padding, you can preserve the initial input resolution. And when you do valid, you're not doing any padding, and then you end up with a slightly smaller resolution on the way outwards. There's some questions. I'm not sure if anything I should pause for.
No, we're good so far.
Okay. Um, so there's a few different parameters that you can toy with in terms of convolution. So you can change the stride. So the first example we were showing, it was just stepping down by one. And so stride, you can change it to two or some other number, and then you're shifting it down multiple places. And kernel size. So the one that we were looking at was initially just 3 parameters that was getting slid across. And you can change this kernel size to be pretty much anything. Um, there's different trade-offs for smaller and bigger. And then the other thing you can mess with is dilation. So instead of taking the 3 that are directly next to each other, you could have 3 that are split by 1 in between each of them. So you're looking at a wider field, but you're not looking at all of the pixels all at the same time. So here's an example. This is doing zero padding, and we have a kernel size of 3, a stride of 2, dilation of 1. So we start all the way at the beginning, and then because our stride is 2, instead of stepping down only 1, we step down 2 actually. So instead of stepping down to x1, we step down all the way to x2. And you can see that this changes the output shape as well. Because we're doing two strides, we're getting half as many outputs basically. So this is a good trick if you ever want to kind of make something more efficient at maybe some loss of fidelity. You can do a stride, and then you're doing half as much work on everything after potentially. Um, and so here's a different one with a kernel size of 5. So we can see that it's five weights instead of 3 this time. Stride of 1, dilation of 1. So it's very similar to what we saw before, just with the kernel size of 5 instead of 3. And then here's an example of the same thing, but with dilation. So you can see that we've got 3 weights, but they're getting applied all spread out. But the stride will make it so it still hits all of the inputs, but because it's spread out further, it's got a wider range of what it's looking at. So looking at the convolutional layers, just the math behind it. We can compare it to the fully connected network. So the convolutional network is only going 1 to 3 because we have 3 parameters. But if we did this fully connected, we would have to go 1 all the way up to the number of input dimensions. And so you can see that this really simplifies things in terms of the number of parameters. You're taking the same parameters and you're applying them everywhere instead of having a parameter for every specific input. So what this is really doing is it's just a special case of a fully connected network. So we're just saying we're not going to connect absolutely everything. We're going to only connect certain subsets. So right now this is an example of a fully connected one. X1 is going to every single hidden unit. And instead, if we look at this, X1 is only going to H2, H1, and then it must have something that's not connected there. And then X2 is going to 3. So this is our kernel size of 3 that's going to only these outputs. And then here's another example, convolution size 3, stride 2, dilation 1, no padding. And this is the same thing where you can see that it's spreading out because you have a stride of 2.
Hey, Ryan,
Um,
can I make a
yeah,
quick comment?
yeah.
So, I liked these diagrams that were in the book. Like I've, I think of convolutions as like one of the mental ways that I think about them is as special cases of fully connected networks, where you can see on the letter D, the bottom middle, it's like I've just tied all the weights on the main diagonal to be the same value, that light brown value. And I've tied all the ones that are right above it to be the dark brown value, and I've tied all the ones below it to be the black value, right? Um, and and so it's like very clear that like a fully connected layer can do anything that a CNN can do. Um, and so I feel like there's a lesson that if you have like the right inductive bias to say, some connections are more important than others, then having fewer connections can actually help as opposed to theoretically you're hurting it because you're removing whatever capability, right?
Yeah.
Um, and then, yeah, um, the stride 2, I didn't have too much trouble picturing, but later on when they get to the transpose thing, that actually really helped me because I never really understood transpose. But then when I saw the picture, it was like very clear what was happening.
Yeah.
So I would just comment on that.
Yeah. Thanks.
I,
Um,
I just
Go
want
ahead.
to say that the idea of taking that this convolution is not a technically convolution. The thing is that in mathematics, many terms are used differently across different topics, across different areas. So I personally think that data scientists should just say that we define convolution in this way and just own it.
Yeah, to be fair, I think the author did have a footnote that said, hey, by the way, mathematicians, I think you call this a cross correlation and it's not a convolution, but there's so many people who do machine learning now that you're screwed because they all call it that. Yeah, there it is.
It's got an
Um,
asterisk saying not really technically convolution. Yeah.
yeah. And then the other thing is like we say linear all the time when what we really mean is affine because we have biases. So if you just had weights and no bias, then it would be linear. But like that ship has also sailed.
Yes, it is just another definition in another area. That's it.
Yeah. All right. So we have this network here. We can see the connections and we can see that same graph that we've been looking at. Um, so we can kind of break this down and understand what all the different pieces are. So let's look at the kernel size. So if we look over here, we can see it looks like 3, maybe 4, maybe 5. And so we can see that the kernel size is actually 5. We've got 5 different weights that we're applying here. And then if we look at the stride, we can see that it's just shifting over 1 every single time. So it's stride of 1. And then dilation, we don't have any dilation. We would see little gaps in between all of these. And then are we zero padding or are we valid? We must be, I believe we're zero padding if I'm understanding this correctly. We would have zeros over here and then it's getting applied over into nothingness.
Yeah, if it was the opposite, if it was valid, then you would see all of them would be 5. You never have any short ones in the ends.
Yeah, yeah, true.
Yeah, I believe the zero padding, and we use padding just to preserve the information, right? Uh, If we don't have padding, we might lose some features. Am I correct here?
Yeah, at
Yeah,
the edges. Yep.
Thank you.
yeah. At the edges, you would have something that looks a little bit probably strange to the rest of your model because you're taking in 3 inputs instead of 5. So you end up with something where you're not using 2 of your weights kind of randomly at the edges.
And one more
Yeah.
question. So strides, that's what I thought, that like sliding a window over the, so do you concur that, or do you have another explanation about a stride?
Yeah, that's how I would describe stride. It's just how much you're moving over the window. So in a lot of cases, it will end up just being 1 or 2. It's pretty rare that it's something other than that. But you're either moving over 1 or you're moving over 2, and you're losing half of your resolution.
Do you have any formula to calculate the stride, or is it just like, what should I say? Maybe like 2 or 5 or 3. It just that's how it goes, or do you have a mathematical formula to calculate that?
The stride is something that you choose for yourself. So you can just set it to 1 or 2 depending on what you want it to be. You control that. So like with this, they just set this parameter to be stride of 1. And it's something that you can tune yourself to try to get the best performance out of your model.
Thank you.
Yeah. All right, so we have another one that we can look at. Um, so kernel size, we can look over here. We can see that all of them are 3 this time. And then the stride, it's still doing the same thing. It's just moving over by 1 every time. And then dilation, it doesn't look like we have any dilation because they're all right next to each other. And then this one, we can tell that it's valid, like Ted was saying, because all of them are 3. We don't have any where it's less. So now we have a third one. So looking at the kernel size, we can look over here and we can see that this looks like 3. Um, stride looks like it's 1. It's shifting over by 1 again. And then dilation, it looks like we actually have dilation this time. So dilation of 2, I believe, is what the value would be. So it's getting spread out between all of them. And then 0 padding or valid, it looks like this time it's 0 padding because it's going off the edge and we're missing these parameters here. Um, there's a question, do we ever want to keep weights of a particular kernel fixed just to make sure CNN see what we think is crucial? Um, I'm sure people have tried that. In general, the CNNs are so good at finding the pattern that you're looking for that if you have any amount of labeled data, you'll probably be better just allowing it to learn the pattern that you're looking for. But there is definitely cases where someone might do something saying like, oh, I think a Sobel filter before will give me the best results because all I'm looking for is edges or something like that. And there's ways that you can do that. I've never personally done that and like said, here, hard code this specific filter and then just always use that. More commonly, I've seen people do that on the input before they even pass it to the network, saying like, okay, I'm just looking for edges or I'm just trying to trace something or something like that. So they just say, this is what my input looks like now, and then the network can do the rest from there. But yeah, it's an interesting idea. I'm sure people have tried it at some point, but I'm not super familiar with that. Most of the time, people just say neural network, do your magic, figure out the patterns. So now looking at channels, so one thing so far we've only been looking at single channels. So we just have a single sequence that's going through time. Um, And so if we look at what this is actually doing, it's kind of just doing a blurring between all of these if we only have a single channel. And then after that, we pass it through a ReLU and then we lose some information as well. So ideally, what we want to do is we want to be able to create additional channels and have that capture all of the different kinds of things that we're looking for. Because if we're limited to just a single dimension, then that's very, very limiting. Um, so people call these channels, they sometimes call them feature maps. Um, and so this is kind of walking through what this would look like. So this is what we have right now. We have these 3 weights, and then it goes to a single output. Um, but alternately, what we could do is we could apply multiple sets of weights to the same input and then get multiple outputs out of them. Or we could just apply a certain size of matrix so that we get 1 input and 2 outputs at the same time. So this is what this looks like when you get these 2 different channels of inputs for a given pixel, basically. Um, so this is what it looks like. You have these 2 sets of weights. So now we have 2 channels, and then we have 2 sets of weights that's getting reduced down to a single output channel as well.
Hey, can
Um,
I just jump in with a quick comment?
yeah.
So when I first learned CNNs, I did not understand this particular phenomenon, this slide. So like you start with a color image, it has 3 color channels, red, green, blue, right? And so when you talk about, we haven't gotten to 2D yet, but when you talk about a 2D 3x3 filter, the diagrams you see, it's this nice little tic-tac-toe box. It's got 9 things that it's looking at. Um, but I didn't understand that because your input is red, green, blue, it has to have 9 of those for red, 9 for green, 9 for blue. So it's actually got 27 weights plus the biases and whatever. So I thought I would just point that out because it took me a while before I realized I had the wrong picture in my head.
Yeah. Um, so looking at receptive fields, so one of the concepts within convolutional networks is if we have this little 3x3 filter, it can only see the things that are directly next to it. And that's not typically very useful. If you were looking at an image and you only got to see 3 pixels at a time, you can't really tell a whole lot about that. But the thing about the CNNs is you're stacking multiple of these convolutions on top of each other, and then maybe have some max pooling or something in between. And what that's doing is it's allowing you to go wider and wider and look at even more input at a time as you're doing more layers, you're doing more pooling, and eventually you've got a convolution that's essentially looking at the entire image all at the same time, or at least a very large portion of it. Because if we were doing just a single 3 convolution, you're just looking at such a limited window that you can find some patterns, but it's not going to be nearly as useful as if you had something that could stack up and look at the entire thing at once. So this is kind of the evolution of it. We have a sequence of inputs, and then we are turning this into 3 channels. So we have this is uh, three convolution with 3 channels. So then it's turning into the same size on this axis, but now we have 3 channels all side by side. And then we can do the same thing again, but this time we're applying it with 4 channels instead. So now we have 4 channels wide. And then we can do this again, but this time we're saying set a stride of 2. And so this will actually have the sequence length on this side, but then we're doing it with a 5 channel. So now we have 5 here. And we can keep going. That's how the all of this stuff stacks up. There's a question, should we calculate that then before we train number of convolutional layers to make sure the last layer sees the whole picture? In practice, people don't typically have to do that. We have so many layers that typically your model is actually seeing more than everything, basically. So it's so many layers stacked up. And if we'll look at some examples of networks later, and you'll see that it like we start with a 224 by 224, and then it's condensed to like a 4 by 4. So the model's seeing the whole thing with just many channels. So we'll look at some network designs later that will kind of show that concept where your X and Y essentially just goes away and the entire thing is represented by some vector at that point. Um, and so it might be something you want to consider if you're designing a very small network and you're custom doing it. But in reality, like all of the networks that are popular have so many layers and such a big receptive field that you don't really have to worry about it. So they're pulling out this MNIST 1D data set again. We looked at this in a previous week. So we've got some flattened MNIST basically, and it's got the 10 different classes, and these are what the inputs look like. And so in a previous week, we looked at the fully connected network and its performance and how its training and test loss and error go. So we can see its training loss goes very, very low. It's able to get perfect accuracy on the training set, but its test set is actually quite high. It's like 40% or something like that. And we can see the training loss, it goes down, but the test loss, it goes down for a while, and then it kind of scoops back up because it's getting more confident in its incorrect answers. Um, so we can contrast this to a convolutional network. And so it'll be 4 hidden layers, three of them convolutional, one of them fully connected, and then a softmax at the end. And the kind of crazy thing about this is it's only 2050 parameters, versus the fully connected one was actually much, much larger. So we'll train it for a long time, and we can look at what the various transformations do to it as we go through. So we start with a sequence of 40, and then we do kernel size 3, stride of 2. So we have our input here. So we went from 40 to probably around 20-ish, and then we must have done valid padding because we end up with one less. And then we're doing this with 15 channels. So we originally started with only 40 inputs and a single channel, and now we end up with 19 inputs and 15 channels. And we can go through multiple more layers of this. So size 3, stride 2, channels 15 again. This reduces it down again. And then we do the same thing. So now we're down to 4. And then we can just flatten this to be 60. And then we do a fully connected layer here. And then a softmax at the end to do our classification just down to 10 outputs. So here's the design of the fully connected network, and you can see the for the CNN, we were only like 2050 parameters, and this one is many times more than that. So in theory, you would think this is a much more powerful network. It has so many more parameters. But in reality, what we see is side by side, the CNN completely smokes it. So it gets very good training performance, it gets much, much better test performance, and it has a tiny fraction of the number of parameters. And this happens because it has a better inductive bias. So we have some understanding of the pattern that we want the model to be pulling out, and we can encode that in the design of the network. So we know that we don't want it to learn specific pixel mappings for everything there. We know that it's able to understand some translations, and being able to do this makes it so that we can build a network that is much more efficient and much more performant, and is actually learning the patterns that we want it to, rather than letting it do anything. Because when you do fully connected, it could theoretically learn the same thing as the CNN, but in reality, it's going to find all of these random other patterns that aren't actually useful to what we want. And that's why you end up with such a higher test loss, despite having more parameters, is that it's learning patterns that don't actually carry over to all of the rest of the scenarios. So now we can evolve into 2D. And so this is really just going, instead of sliding it across one axis, let's slide it across two axes. So you go left to right, and then when you get all the way to the end at the right, you might slide it down one step, for example. And so that's something where you can have strides that are actually different on different axes. So you could say stride 1, and you're just sliding left to right 1, and then when you get to the end, you slide down 1. Or you could do something where you have strides of 2 and 1 or 1 and 2, for example, and then you're doing different stride lengths on the different axes. Um, so here's what this looks like. And so we can see this is the filter now. Instead of just being a single flat set of weights, you can have it be two-dimensional, and then this will be applied to the different blocks of this. So we have 3 weights, so it'd be applied to this certain subset over here, and then we might slide it over 1, and then we're doing this subset over here. And so it's very much the same concept. You're just doing it in an additional dimension, and you can extend that to any number of dimensions. So I've been doing a lot of stuff with volume data lately, and so it's the same exact thing. Instead of 2D convolutions, we had 3D convolutions, and it's just one more dimension added in. So you have to mess with the height, width, and the depth. Um, but in practice, it's exactly the same thing. It's just kind of adding an extra for loop to what you're doing on another axis. Um, so this is what it looks like in practice when you have an RGB image. So this is what Ted was talking about earlier. So pretty much all of our images will start as 3 channels. So you have your red, green, blue. And so the 3 by 3 that we saw will most likely actually be a 3 by 3 by 3, because you also have to have the additional one for the channels, because it has to look at all of these together. Um, and so um, this can this one looks like it's actually looking at this specific region, and then it's taking this whole thing and summing them to have a single final output. Um, so it came in as a 3 by 3 by 3, but then it just became a 1 in the final eventual flattened output. Um, um, so in in most convolutions, there's various different operations that you would want to apply to them. Um, and so one of them is downsampling or some form of pooling so that you can see larger and larger regions. So in theory, you could do a 3 by 3 convolution and you do that 30 times, and then by the end of it, you've seen all of the different inputs of the image, but you have to stack a whole bunch of layers to eventually get to that because the 3 by 3 is actually only extending your receptive field so much. So a more efficient way people have figured out to do this is through some of these techniques here. So downsampling, for example, is just what you would expect from images and other techniques where you're just directly saying I have a 4 by 4 and I'm going to reduce it down to a 2 by 2 and I do some form of downsampling there. Max pooling is another option. So saying I'm going to split this into 2 by 2 grids and then I'm going to take the maximum out of them. So we can see that the max of this one was 6, the max of that one was 8, the max of that one is 4, and the max of that one is 8. And this gets reduced down to this. So this is a very common one. Lots of models use max pooling. Another one is mean pooling. So in this one, you're just saying I'm going to take the mean of this 2 by 2 grid and this 2 by 2 grid, and then you end up with these outputs here. So max pooling and mean pooling are very common, and the advantage of this is it still gives you that invariance to things being shifted a tiny bit, but you don't have to do a whole bunch of convolutions all stacked together. It's very efficient at that.
I have a
Um,
question for you.
yeah,
So in real life, is this like average pooling or mean pooling? You think that would be a little bit more beneficial or give you more accuracy than max pooling? What is your experience, or is it trial by error?
I think in reality it doesn't make a huge difference because your model is learning which values to bring up and bring down. So in reality, in these small local areas, your model's probably lighting up high for all of these and maybe low for all of these, and it's learning that pattern itself. So whether or not you're doing max or mean, um, it 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 makes a relatively small difference. And people have done studies of this to figure out what the best results are. And there's been a bunch of Kaggle competitions where people have said, I train this model max pooling, I train this model mean pooling, and then I just average them together. And if I look at them side by side, they both do relatively the same thing. Um, so I wouldn't really stress over which is which. Um, yeah, I mean, there's slightly different things going on, but in practice, you'll get relatively similar results most of the time.
Thank you.
Um, so we had downsampling, now we have upsampling. So you have something that's small and you want to make it larger. You can do something like this where you just broadcast it. So some sort of nearest neighbors upsampling where you just say, if it was a 2, just make it more 2s. If it was a 4, make it more 4s. And then you increase the resolution there. Um, you can do max upsampling. I haven't really seen people do that in practice, but um, and then bilinear interpolation. So just basically saying I'm gonna scale this up with bilinear interpolation. And these are kind of interesting because you can do all of these in PyTorch and it will still keep track of all the gradients and stuff for you. So I don't exactly know how all of the mechanics of that work, but I one of the competitions I did a while ago for the contrails one, it was very, very small, little, like 1 pixel, 2 pixel wide strips. And just your choice of interpolation was actually important because if it made more jaggy edges for you, that was bad. And so it was very convenient that the PyTorch layers, you could directly just say do interpolation and then it would just do it and it could optimize through bilinear interpolation and stuff like that. So um, just added color. I've had a scenario where that was actually important. Um, so here's what Ted was talking about earlier. So one of the other ways that you can increase resolution is with these transposed convolutions. So it's kind of the opposite thing where when you're doing the convolutions, typically you're reducing down the resolution. But with this, what you can do is you can actually increase it. So you're doing the opposite operation. Um, so we have a single input and we're passing it to two outputs, for example, or three, depending on the kernel size. So this is doing the opposite operation from here. So this is reducing the resolution down to 4, and this is going from that 4 back to a higher resolution. So here's a this one was kind of puzzling to me for a while. So one by one convolutions. There was a whole lecture on this when I was first learning from the Coursera course, and they had a like 10-minute video on one by one convolutions. And I didn't really understand what the benefit of them was. Because if you look at it, what is a convolution? It's just a single unit. Why would you want to apply a single unit to your entire input? But it's not really a single unit because you're looking across all of the channels. So these one by one convolutions are actually really good ways to find the interactions between all of your channels. So you don't, these are for when you don't care about the spatial element, you don't care about the XY, you just care about learning the interactions between all of the channels that you've created. So typically with these networks, what you do is you go smaller and smaller on the XY until you have basically a tiny little vector almost that represents the meaning of your image. But then you can do these one by one convolutions, and it allows you to find the interactions between those. Um, so like they're saying, it can mix the channels, and it's also really useful for changing the number of channels. So there's certain networks where you have something where you go, oh, this is a 512 and this is a 32 and I want them to merge now. And so you can do a one by one convolution to say, take this 512 and make it a 32. And then now I can just add them or something like that. So one by ones are actually used extremely commonly in a lot of these networks because it's kind of almost a utility thing saying I don't care about the XY, just change the number of channels that I have in some intelligent way. So merge these or expand them so that I can line things up in terms of dimensions. So on image classification, one of the things that they were pointing out is you have all kinds of different characteristics of these images. So you can have different rigidity or number of instances. So like this one, you can see it has a bunch of, looks like strawberries maybe. It's kind of blurry. You can have a lot of clutter. So they're trying to find a steel drum here, and it's only here, but you have all of this other stuff going on. There's different size of things, textures, and so the ImageNet data set is actually pretty difficult because you have all of these other conditions going on. So you have over 1 million training images, 50,000 validation images, 100,000 test images, and we have 1,000 classes. So if you actually break this down, we don't have very many examples in the validation set for all of these different classes. So you're judged kind of harshly sometimes. Um, so here's AlexNet. This is kind of the genesis of all of this. This was the point where people go, wow, this like neural network stuff is actually amazing. It can learn all of these patterns and it does so much better than all of the stuff that we've done before. So this is taking the 224 by 3 that we've talked about. So it's got the certain XY resolution, and then it's got 3 channels. Um, and then it's doing a 11 by 11 convolution. So this is much bigger than any of the ones that we've looked at before. So it can actually take a pretty sizable block out of it. And it's doing stride of 4, which is quite large. Um, and what this does is it makes it much, much smaller right off the bat. So you're doing these big 11 by 11 convolutions, and we're doing it out to 96 channels right off the bat. So we've got now an XY resolution of 55, and we've got 96 channels, and then they do max pooling on top of it. And so now we're all the way down to 27 by 27. They do a 5 by 5 convolution, and that expands it to 256. So we've already gone from 224 down to 27. So we're almost 10x smaller, and we've turned all of the XY resolution into a whole bunch of channels that can capture a ton of different stuff that we're looking at. And so they continue down this process, and we can see at the end they're all the way down to 13 by 13 by 256. And so this is what I was talking about earlier, where you don't really have to worry about seeing the entire image, because we've gone from 224 by 224 down to 13 by 13. So it's this tiny little thing at this point. So we know that everything there has been very, very strongly compressed. It's all together. So we could go all the way down to 1 by 1, but in practice, like 13 by 13 is already small enough that you've compressed everything down to this tiny, tiny little image that has a ton of channels that can represent all of the different things that you're looking for. Um, and then what they do is they flatten this, and then it becomes a bunch of fully connected layers. So now they have 4096, 4096, and then another fully connected layer that goes from 4096 to 1000. So this is all of the different classes, and then they apply a softmax function. And so now we have our 1000 different probabilities for all of the different classes that we're trying to predict. Um, so this initial design was 60 million parameters. So if we look back at the original slide saying 224 by 224 was going to make a 22 billion parameter model, this is like orders of magnitude smaller, and it gets us better performance actually. So this adding these convolutions was a big breakthrough. Um, so during their training, they did a whole bunch of augmentation. So we got, or the ImageNet set is 1 million images or a little bit more than that. And what they did is they did a huge number of augmentations. So you could do the original, you could do the flip, rotate and crop, vertical stretch, color balance, blur. You want your model to be invariant to all of these things. So if you make some slight alteration, but it doesn't change the meaning of the image, then you want your model to output the same thing again. And so they're saying a factor of 2048. So they took that 1 million images and they did 2048 times that. So huge scale of images, because they did augmentations of all of them, a whole bunch. And that made it so that their model was very, very robust to all of these different conditions that you might occur. So they added dropout, just this premise of let's blank out some of the weights during training so that they don't get any gradient and they don't have any calculation in the forward pass. You can see like they just say turn off this neuron, and then try to train with these neurons off and still get the right answer. And so there's a lot of different ways of thinking about this. What some people describe it as is like taking an ensemble. So you're saying, I'm going to take a whole bunch of different subsets of these weights and train them all to be successful. And then when you do the full, like everything turned on, then you have all of these networks kind of ensemble together. Um, there's a bunch of different ways of thinking of that, but that's just one way that might be useful for you guys. Um, So here's the details of this. They trained with SGD with certain momentum parameters, and they ended up getting a very, very good result. So they don't have a comparison point, but this is massively better, like half the error rate of anything that had been done before. So this was a big breakthrough. Um, and then few years after this, they people tried out a whole bunch of different networks and they came across this VGG. Um, and it's very similar, but it's just an optimized network of the similar principles. So they did 3 by 3 convolutions, max pooling a few times, and then at the end we get to 14 by 14 by 512, and then they do the same thing of let's flatten this out and then do a few linear layers. Um, so if you actually look at this, it's not very far removed from AlexNet. But the interesting thing about this is it more parameters, more layers, and then they got a much, much better result. They basically halved the error rate of the previous network. Um, so we can see starting in 2012, much, much better result. And then going all the way to 2014, 2015, they cut that rate again. And then this is the progress as things have been going. People have pushed this further and further and further, to the point that we some people consider it almost a solved problem because we're so good at these image classification tasks now. Um, So moving on from image classification to object detection. So we showed earlier there was that slide where it was saying find the bounding boxes of the specific animals and person and bike. And so you have a bounding box for all of these different things in an image. You're not just saying what's in the image, you're also asking the question of where. And so this YOLO paper has been very, very popular for a long time. We're all the way up to YOLO V8. So people have continued to iterate on this, and that's largely been the standard object detection network for people who want stuff that's fast and performant. Um, and what they do here is they split it into 7 by 7. So we have all of these sub images basically, and then wants to predict a class at each of these. So predicting a class here and here and here. Um, and then on top of that, it's also predicting bounding boxes. And so the way that it does this is it actually outputs an XY coordinate, and then it's also outputting the height and the width, and then a confidence as well. Object detection, if you actually dig into it, there's a whole ton of stuff going on there, that's very specific to object detection. So there's non-max suppression and region proposal, and people have really, really dug deep on this topic, and there's lots of stuff to play with. Um, so this is like what they're saying here, heuristic at the end to threshold and decide final bounding boxes. Um, so this is showing the initial thing split into 7 by 7, and then they have the classifications, and then a whole bunch of potential bounding boxes, and then they have something that will try to classify each of these bounding boxes individually, and then they have to figure out which ones are actually the best, the highest probability, and then they have to condense them down and say like, what's the final result? What's all of these bounding boxes condensed into a final answer? Um, So people have figured out that you can do very good transfer learning from a bunch of these different tasks. So if you actually train a model on ImageNet, then you can take that same model, those trained weights, and then apply it to segmentation or object detection or depth estimation or many, many different things. And it will actually get better results than if you just tried to train it from scratch. So whatever it learned from the initial ImageNet classification training is also useful for other tasks. And so a lot of people have continued to improve on the image classification stuff. So that graph that we saw where performance and error is going further and further down, that's very, very useful because it helps all other related tasks too. If you can get better ImageNet performance, then you can probably also get better semantic segmentation and object detection and anything else that you could do with images as well. Um, so here's final results. You can see it's outputting not only the bounding boxes, but also the classes that are inside of those bounding boxes. So it's finding people and horses and dogs and there's a question, are there any guidelines as to how we should modify it, which layer? Um, I think it I think it depends. I think at this point, a lot of these networks are so well optimized that for most use cases, you want to use something that has already been researched and determined works very well because it's been a decade plus of people trying all kinds of things and figuring out what works. So my recommendation is not even worry about modifying at this point. Just figure out like what is the state of the art or what fits your specific parameter set. So something that I commonly do is there's the PyTorch image models library, and that has hundreds of different models, and it has the full range of extremely high accuracy, but very, very slow, and extremely small, but highly performant, can get like hundreds of frames per second out of those models. So what I typically do instead of trying to design something on my own is I will go and I'll look through the listing and say what kind of fits the parameters that I'm looking for. Um, do I care about speed or accuracy or something else? And then I'll use that as a starting point. And then at that point, you might have something that you can modify on it. But I would say at this point, most of the decision comes down to doing the research on what's state of the art right now, what can get you the best results out of the box. Um, in reality, most people aren't doing individual tweaks of layers and stuff at this point. But it also depends on the application. So if you're doing a problem that already has a lot of exploration on it, like image classification, then that's possible. But if you're doing something that has some weird format of data, then you might have to end up doing something more exploratory. So right now I'm working on that scroll stuff still, and I have a whole bunch of volume data, and that's a little bit different from the all of the image-based stuff. But even then, what I've done is I've taken off the shelf, like here's a 3D UNet, and then figured out how do I make this fit into my specific shape of input and output. And it's worked well for me, basically reusing that 3D UNet for a lot of different things because it's a successful architecture that can be reused for a lot of different things. Um, moving on to semantic segmentation. Um, so this is the task that we were talking about earlier, where you're saying I want to get a pixel mapping of the classes for every single pixel in an image. So we have this network here, and they split this into an encoder and a decoder. And if we look at this, this is very, very similar to the VGG one. Um, so this step they call an encoder because we're going down to a much smaller representation. We're making an encoding. So we end up with this 14 by 14 by 512, and then they flatten it to be 4096. And then they do a fully connected layer. So they look at the interactions between all of those 4096. And then on the flip side of that, we do all of the deconvolutions and max unpooling And then eventually we build all the way back up and we decode that thing that we just encoded. So we take this 4096 and we build it all the way back up into the initial 224 by 224 by 1 or 3 or however many classes that we have on this output. So we can see what this looks like, the input, we have this horse, and then we want it to be able to find um, the uh, the horse outline, basically, all of the pixels that are horse, and then we can see what the model is actually able to output, and it does a pretty good job. And we can see uh, this is a binary case. We're just looking for the horse, but we can also look for multiple things in a specific scene. Um, so looking for cars and people and everything else. So now looking at residual nets. So one of the problems that people realize is if you go deeper and deeper and deeper, eventually you end up running into these problems where it's difficult to train these models. Um, we saw this pattern of like, okay, when we do 4 layers, it's not as good. We do 5 layers, it's a little bit better. But if we do 500 layers, then all of a sudden we run into problems, and it doesn't. We can't just do more equals better. We have to figure out some trick in order to get it to actually work out. So we can see that in this case, 20 layers beat 56 layers. And so the trick that people figured out, this is what a regular network looks like. So we just say X is going into F1, and then that's going into F2, and then F3, and then F4. And what people realized that you could do is you could make these residual connections where you're basically just passing the input over these different layers. So we have, for example, let's say we have our 224 by 224 image that goes into this layer. Um, and then we get some output there, but we also just directly pass it over and we just add it back in, or do some other operation. And then what that allows us to do is maintain the information that we initially had and add some additional learned representation on top of it. Um, and so this allows the gradient to pass through much more quickly, and we pass the identity through. Um, so people found that this allowed us to train um, much deeper networks without that problem of like beyond a certain point, we just couldn't train them. They weren't converging. Um, so one of the things that they're pointing out here is that the order of operations is actually important. Um, so in these residual connections, depending on how you're passing the information forward, um, you can do things in all kinds of different ways. So you could say, let's take my input and pass it through these layers, and then also pass over the initial all the way past it, or we could have everything pass through the linear layer and then get skipped around and do the ReLU and linear. Um, and we can do multiple, and then we can pass it over the top and then do batch norm. There's all kinds of different permutations of this. We can do these all in different orders, and they actually do have an impact that makes a difference. Because if you really look at this, um, ReLU is um, ReLU is losing us some information. So if you put it all the way at the beginning, you're losing information before you even do any operations on it. Um, and so eventually people figured out various different successful blocks. So you can do things in a lot of different ways. And people might do something where they say, I do 2 convolutions and then I do a ReLU and then I do a batch norm. And even within that, I don't know that there's a ton of consensus on exactly what's best. But I remember in some of the earlier days, people were like saying like, oh, it did 2% better, it did 3% worse, and it was just the ordering of these things. And so they do actually have an impact, and people have figured out like what is the correct way to do this. So after figuring this out, people scaled it up, and they said, now we have this trick that allows us to train uh, much better, much bigger networks. So let's scale it all the way up to 200 layers, because before we couldn't even do 50, it wouldn't even converge. So now we have this trick that makes it work, and then we scale it up to 200, and we get way better performance than we did. And we got back to the performance where it was like, okay, just more equals better. If we scale this up more, we're going to continue to get more performance. So that was a positive thing to say. As we get more compute, we can get even more performance. Um, So before we were looking at the semantic segmentation model, that was just a basic encoder decoder model. And then what people realized was even better than that was this UNet architecture. And this is very, very common. Like it was invented in 2016, but it is still to this day used in like almost every semantic segmentation problem. So definitely worth looking into and understanding a bit if you're ever tackling these kinds of problems, because it's still very relevant. It's something that has stood the test of time. Um, so the way that this works is we have 572 by 572, and it's input, and it's going down, 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 down in size on the XY axis and going larger on the channel size. So there's a bunch of convolutions, max pooling, and then we get all the way down to here where we have essentially a small XY, many channels, and then it starts going back up to this final resolution. But the big difference is the connection that is spanning these. Um, so people realize that this condensed representation here is very, very good at understanding the image, but it's not very good in terms of spatial understanding. So what people figured out you can do is you can take um, basically residual connections across these various gaps, and then you can pass it some more of the initial input. So if you give it this image here, it's got the full resolution. This is what the image looked like again, and you can pass it all the way over to the end. And so you have your representation that was like, what is in the image? And then you have another that's saying like, here's the initial details, and then paint it back on to say, here's what the individual pixels meant. And so this unit architecture has been very, very successful because it combines that condensed representation with the actual the spatial details of the pixels in the original image. Um, so this is particularly strong at like all of the medical imaging and cell biology stuff. So here's an example where they're taking this thing that needs very fine-grained classifications, and so you have all of these cells here, and you can see um, here's the different kind of tiny little specific predictions it's able to make because it's given that condensed representation and the full resolution again, and it's able to merge those to kind of map all of the different things together. All right, I think that's it. Any any questions? I know we're a little bit over time, but still room for a question or two.
There was some discussion in the chat, but nothing I think that you need to stop and answer. One high level comment I wanted to make is that if you look at like from AlexNet and VGG, so you're talking like 2015, you saw this thing that said that like, oh, a CNN has many fewer parameters than a fully connected network. This is what like Ryan's been emphasizing, right? So the idea is if you have the right inductive bias, then you can build a better model. I think this translates to tabular. Like if you do good feature engineering, you'll get better results. Okay, so that's true, and like you should definitely like keep that lesson in your tool chest or whatever. But like the other lesson that I think we've learned more recently is if you have massive amounts of data, if you have like internet scale data, then you can take something that's completely generic and it will learn the inductive biases that it needs to learn. You don't have to handcraft them. So you saw that progression with AlphaGo, where they started out with a lot of rules of the game and things, and then they were able to say, "Oh, we learned this, and we were able to modify it to play chess and do other things." And then came Alpha Zero or whatever they called it, where basically they're like, "Nope, we gave it no information. We just had enough training data that it was able to learn stuff." Um, and then you see things like um, whether it's transformers being used for vision or for other things. The caveat, though, is you do need this ridiculous amount of data um, in order for it to not just learn the signal, but learn the rules of the game as well. So it tends to be kind of two different use cases, right? If you're working for a company and you have some small thing you need to do, you generally aren't going to have tons of data and you're going to use pre-trained models as starting points, and you want all the inductive biases you can inject into it with good feature engineering, good everything. But if you're at a research lab and you're trying to build state-of-the-art, GPT-5, then you're not going to follow that playbook. You're going to do the other thing where you're going to get as much good, clean data as possible and just let the model learn its own rules.
There's a question about, is the UNet same as inside of stable diffusion? I believe it is. I haven't looked at stable diffusion in a ton of detail, but I believe it is.
It may not be the exact same size UNet, but it is that architecture where you see CNNs shrinking down and then going back up with skip connections. Ultimately, stable diffusion, you also have this wrinkle that we do text guidance. So there has to be a third input, which is your text. But the basic architecture is exactly the one that Ryan showed you.
All right, great. Thank you, everyone.